challenge and motivation behind this project. And next, I will present the key outcomes and the results from each publications during the course of this research. And I finally will summarize the work with a conclusion and discuss the future work. And first question you may ask me, what are metal cutting tools? So metal cutting tools include inserts, small and replaceable tips made from some of the hardest material in the world, and that cut the metal materials efficiently. And then this insert is mounted on the specialized tool head designed for different material and cutting operations. And the metal cutting tools also include these solid round tools used for drilling, milling, threading, and so on. And then this tool is mounted on the tool holder, which is attached to a CNC machine where the cutting process happens. Next, why do we use them? Across a wide range of manufacturing industries, including aerospace, automotive, oil and gas, power generation, and many more, engineering and components manufacturing heavily rely on metal cutting tools. There are a vast number of cutting tools existing in the world, and widely used in turning, milling, and drilling operations in the manufacturing industries. And these tools allows us to create a wide range of features upon the workpiece material, from simple shapes to very complex components. And in this project, the methods and the models are developed to be general and applicable to all types of metal cutting tools. And to demonstrate the concept idea, we focused on a specific example, according to that used in internal turning operations. In this application, the workpiece is mounted on the spindle inside a CNC machine. And the cutting tool is assembly, including the insert, tool head, and adapter. And this assembly is mounted on the tool holder, which is attached to the turret system of the CNC machine. And turret system rotates to position and index the required cutting tool for the machining operation. The cutting conditions at the tool tip dictate many aspects of the final component's quality. Tool tip deflection, for instance, will influence the geometrical accuracy of the machined component. And in order to measure these conditions in real time, the cutting tool is equipped with sensors in the tool body. We add accelerometer to measure the vibration, ideally placed as close as possible to the tool tip, where the vibration amplitude is highest. And we add a strain sensor near the clamping area, where the strain level is highest. And this sensor captures the strain data used to estimate the cutting force and the tool tip deflection. And sensor data is transmitted wirelessly to the computer through a Bluetooth antenna. Here we have a sensorized tool available today. Actively cutting the workpiece material. And during machining, the true signal from tool tip will be captured by the embedded sensors, saved as a digital data, and send the data back to the computer for real-time monitoring the cutting loads and vibrations inside process. In this project, we're aiming to extract the high-quality information during the machining, such as cutting force, tool tip displacement, and tool condition, which is correlated to the tool wear on the insert. And this is made possible through the data collected from the embedded sensors. And why is this important? Because the data allows the system to make automated and intelligent decisions, improving the efficiency, quality, and the tool utilization. For example, we can stop and retract the cutting tool when the critical tool wear is detected to protect both tool and the workpiece. And we can track and document tool wear over time, supporting a predictive maintenance and quality assurance. And we can optimize the fade rate in real time based on the tool wear condition. And we can monitor the surface quality and the components dimensions during machining, reducing scrap and rework. And we can even estimate the remaining tool life and adjust the process accordingly to maximize the productivity. So instead of the passively collecting data, this sensorized cutting tool becomes the part of a smart and adaptive system, driving the performance and process reliability from within. However, several challenges remain for this type of products. First, there is no clear separation between the process-induced loads and the loads caused by the tool wear. And tool wear addressed in this project is tribological driven, arising from the friction between the cutting tool and the workpiece. This affects the cutting forces. Unfortunately, an accurate model describing the relationship between the cutting forces and the tool wear is still missing. And another challenge is that the measured data is colored by the dynamic effect of the tool structure. By that, we mean the true signal transmitted from tool tip to the sensor will be influenced by the dynamic properties of the transfer path, leading to a distortion and a reduced accuracy in the measurement data. Additionally, the strain sensor used is statically calibrated, meaning it provides the accurate results only under the steady state loading conditions. And this is insufficient to predict the dynamic loads during the machining. To address these challenges, I have structured my research around 3 research questions. And first question explores, how can cutting force modeling enhance the interpretation of sensor data to distinguish the contributions of cutting process and the tool deterioration? Second question focuses on, how can the data from sensor-equipped cutting tools being used to accurately estimate the dynamic loads and tool tip deflection while accounting for the dynamic effect of the transfer path between the tool tip and the sensor location? The last question investigates, how can the integration of advanced modeling, signal processing techniques, and sensor-equipped cutting tools improve data quality, enhance measurement accuracy, and enable more precise real-time monitoring of cutting machining conditions? And this question is particularly big, and it spans the full scope of this project and ties the work together. And to answer these questions, this project has been organized into 3 work packages, each forming the foundation of the publication. Research methodology. In this project, we adopted a hybrid methodology that combines the DRM and a coordinated approach to enhance the research effectiveness and adaptability. And the DRM utilized to define the research problems and identify the gaps and establish relevance areas and set a clear objective for this project. Coordinated approach provides a foundation or framework to foster multidisciplinary collaboration and aligns the research activities towards a shared goal. By integrating these approaches, we can streamline our research process and enabling a rapid processing and adaptive planning based on the new research results. The first publication is about a prediction of a cutting force using an extended Keynes-Salam force model, incorporating the two flank wear progression. This work is driven by two motivations. First, we need to develop a model that accurately captures how the cutting forces change as a two-wear progression during machining. And this model will become a crucial tool for the real-time monitoring of two-wear based on the high-quality force data from the sensorized tool. Although most cutting operations are three-dimensional and complex, but we use this two-dimensional orthogonal cutting operation to demonstrate the basic mechanics of the metal removal, where the cutting tool moves perpendicular to the workpiece motion. If we pause this process and put the focus on the flank face of the insert, a two-wear length appears on the surface, defined as the wear length VB. By tracking this VB value over time, we could generate a two-wear progression data set. And this data is crucial for building and validating the predictive model for the two-wear. The existing Keynes-Salam prediction model defines the relationship between the cutting forces and the width of cut B, uncut chip thickness H, and the two-rig angle gamma. We extended this model to account for the variations in the cutting force as the function of VB. And to define unknown parameters, which is highlighted in yellow, we designed a cutting experiment with the specific two workpiece combination. And in a test matrix, it includes 4 different fade rates to vary the uncut chip thickness H, and 4 different cutting insert, each with a unique rig angle. So this resulted in 16 cutting tests, generating a data set of cutting forces and corresponding two-wear across the time. And this data set is then utilized for regression analysis to define the unknown parameters of the model. All the cutting force data collected over the two flank wear VB from that test matrix has been plotted in these figures. By analyzing this data, we determine its unknown parameters values for the model, allowing this model to best fit this experimental data. And to validate this model, we carried out a 3-dimensional longitudinal cutting test, as you can see in this video. And to ensure the reliable results, we used the 2 different cutting inserts. However, the model developed for this 2-dimensional cutting is not directly applicable to the 3-dimensional case. And to bridge this gap, we utilized a transformation model that adapts the 2D mechanics to the 3D. And here is how it works. First, we discretize the cutting edge into smaller segments, considering the nose radius as well. And then we apply this two-dimensional carding force model to each segment individually. And then we project the segment force into tangential, radial, and axial directions. And finally, we sum them up to obtain the total force components in each direction. And this is the result. And the result shows the estimated shows a good agreement between the estimated and measured carding force components in each direction, highlighting the model's capability to accurately capture the variations in the carding force induced by the tool wear. And importantly, this model becomes a crucial tool for real-time monitoring of the tool wear later, once the high-quality force data from sensorized tool is available. This publication focuses on the carding force estimation in metal carding tools, a study on the sensor-equipped cantilever beam, and two motivations behind this project. First, we need to enhance the data quality and reliability. We need a model to capture the dynamic properties of the transfer path between the tooltip and the sensor location. And we also need a model-based approach to efficiently and accurately estimate the input force by using the string data measured from the sensor. To achieve this, we use a simplified case, a cantilever beam equipped with a strain sensor near the fixture. And this table shows the specification of the beam used in this study. So we begin with Euler-Bernoulli beam theory with the standard equation of motion that I assume it is known to most of you. By solving this equation, we could define the transversal deflection model shapes and undamped natural frequencies. And then we determine the model mass based on the model shape scaling. And next, we can define a conventional deflection force transfer function expressed by its model superposition, where the residues and the poles can be determined from this model shapes, natural frequencies, and the model mass. However, our target is to define the strain force transfer function, not just the deflection to the force. So to do that, it is important to understand the relationship between the transversal deflection and its corresponding strain. In this picture, we have a beam at its initial state. If we put a focus on a segment, which is unchanged, now if we load the beam by a force at the free end, the segment is deformed with the angular deflection theta, expressed by the equation number 6. Rearrange it, and applying the curvature formula, we derived equation number 8 that tells us the strain is proportional to the second derivative of the deflection. And importantly, this expression is space-dependent only, allowing us to calculate the strain model shapes directly from the determined deflection model shapes. And smaller figures shows the visualized model shape for both of them, for the first mode and the second mode. Now with this model shapes, we can update the conventional transfer function to our desired analytical model. To validate this analytical model, we use the following setup. We have a shaker to vibrate beam from the free end, and force sensor measures the input force as a reference. and the strain response will be captured by the strain sensor near the fixture. This figure shows the measured strain FIF. If compared with the result from our analytical model, a discrepancy has been captured, and the difference arises from a more flexible boundary condition in the experimental setup compared to the ideally fixed condition assumed in the analytical model. To improve this correlation, we extracted the first natural frequency and the damping ratios from this measured FIF. And the first natural frequency will help us to calibrate the model parameters, which is correlated to the beam's physical properties by the following equation. Quickly adapting the model to the real setup, and damping ratios will help us to correct the magnitude of the model. Now we have this developed transfer function describing the relationship between the input force and the strain response, accounting for the dynamic properties of the transfer path. And to enable efficient computation by using the sampled strain data, the transfer function is identified as a digital data by the following equation. And by applying the inverse of this filter, we can accurately estimate the input force from the measured strain data. However, the digital filter representation of the transfer function is not always invertible due to its inherent properties. As you can see in this zero pool plot, the original transfer function contains the zeros in the outside of the unit circle, leading to an inverse filter unstable. To resolve this problem, we convert this digital transfer function into its minimum phase equivalent, ensuring all these zeros and pools stay inside the unit circle, and then stabilizing the inverse filter. To evaluate this transformation, we conducted a frequency response analysis on the combined transfer function, which is the product of original transfer function and its minimum phase inverse. And results showed a unity magnitude, confirming the accurate transformation. And importantly, the phase response X-space approximates linear phase until 650 Hz, defining the feasible frequency range for the inverse filter. And to avoid the amplitude distortion caused by the nonlinear phase response at high frequencies, we need to apply a low-pass filter with a cutoff of 650 Hz to the inverse filtered signals. And we use the same setup to evaluate this model-based approach for estimating the input force. To emphasize the importance of this approach, we conducted a comparison test where we're using the statically calibrated strain gauge to predict the input force and without considering the dynamic transfer path. And the result shows at very low frequency, this model captured the reference well, but at higher frequencies, a significant amplitude and phase distortion deviation appears. When applying the model-based approach, the amplitude deviation has been significantly reduced, but a constant time delay still remains in this result. And this time delay is caused from this linear phase response of the transfer function. But we can calculate this time delay by this equation. and use this one to compensate our result, leading to a more accurate force estimation overall. And this work is an extension of the previous one. And the motivations are, we still need to evaluate the model-based approach by using a physical sensorized cutting tool. And we need to investigate if analytical model can be calibrated to the two configuration using only the measured strain response data. And we need to evaluate if both impulse input force and two-tip displacement can be accurately estimated from the measured strain data. So now we have this physical cutting tool equipped with a sensor near the clamping area. And the calibration stage has been presented in the previous work. In practice, each cutting tool requires its own calibration, but the two users rarely have the access to the equipment needed to measure its excitation force, and this makes this calibration process challenging. To address this limitation, we proposed a practical alternative. So we're applying an unknown impulse load at the free end, like this. And we use the sensor to capture this impulse response. By applying a Foster Fourier transform to this measured response, then we convert the signal to the frequency domain. And the first natural frequency is identified at the first dominant peak in the resulting spectrum. And damping ratios can be estimated by using this logarithmic decrement approach. Based on the peak values extracted from the selected periods of the impulse response. Once the K model parameters are determined, and the analytical model can be quickly adapted to the according to setup, allowing us to generating the accurate transfer functions, crucially for this following steps. One such transfer function has been shown in this figure, demonstrating the good agreements with the measured reference. And this slide will illustrate our model-based approach for estimating the input force and also the two-tip displacement. So we start using this measured strain response to estimate the excitation force through a transfer function, inverse transfer function. And then apply this estimated force to another displacement force transfer function to predict the two-tip displacement. And this process forms our co-routine of developed estimation method. To validate our method, we use this experimental setup. We have an impulse hammer to excite according to at the two-tip and measure the input force as a reference. And we have accelerometer installed on the opposite side of the two-tip, and the strain sensor is mounted near the clamping area. In the experimental test, the cutting tool is impacted by the hammer at the two-tip, and the excitation force is measured. If we utilize the measured strain response, we can estimate this input force through an inverse transfer function. And results shows a good accuracy in this force estimation by using the proposed method. And then we utilize this estimated force, applied it to a transfer function to estimate the two-tip displacement. And however, the displacement sensor was not available in the lab at the moment. So we have to use alternative way to validate this estimation. In that way, we utilize the accelerometer data and generate the accelerance FIF and calculate it to this displacement FIF, which will be used to fit a state space model in the MATLAB. Once a good match is achieved like this, and this model can be utilized to simulate the displacement response for any given input force. Now, if we apply this measured force from the hammer to this model, then we generate a reference to compare with the estimation result for displacement. And the result shows the proposed method accurately captured the two-tip displacement as well. Some discussion. So the first research question has been fully addressed in the first paper. And paper 2 and 3 handled the second question. And the final research question is partially explored in this thesis work. And it will be fully addressed in my future research work. To conclude, this project explores how we can combine the sensorized coding tool and analytical modeling signal processing techniques to improve the accuracy in the machining environment. So we developed a coding force model that include the toolware, enabling the accurate force estimation and real-time monitoring of the toolware. To address the dynamic distortion between the two-tip to the sensor location, then we proposed a strain force transfer function, and combined with inverse filtering, it allows us to accurately estimate the input force based on the measured strain data. All these methods and models were validated through a controlled lab tests and demonstrating the strong agreements with experimental results. And this provides us a solid foundation for applying this method and models to the future sensorized coding tool applications. And going forward, the method needs to be extended to handle more complex dynamics, including more degrees of freedom. And the real machining tests by using this prototype sensor-equipped coding tool are still essential. And it should be validated by using the high-grade sensors as a reference. And finally, since the embedded system often produced a low-quality data, so the proper signal processing techniques is crucial to helping us to accurately investigating the input force and two-tip deflection, and also for the real-time monitoring during machining. All these steps will help us to advance the next generation of smart coding tools towards the real-world industrial applications. And this concludes my presentation today. Thank you.
Thank you. So let's do a 5-minute break. Be back here at 10:43. And while we do that, we make sure our opponent is ready and also respondent. Okay.
Men den just follows the
When I saw, yeah, when I saw myself.